All right, well, hello, Honors Algebra 2. This is the second day of Unit 12. We got a little bit of a preview of this section in the previous section in 12.1. Today we're going to be focused solely, though, on verifying trig identities. So we need to start off with the question, what does it actually mean when we are verifying a trigonometric identity? What we're trying to do, what we want to show, is that one trigonometric expression is equal to another. In other words, we will have a slight difference from what we saw in 12.1, which I'll take you back to very briefly. In 12.1 example 2, we did some work with trigonometric identities, but we were only working with a single expression. So we were just working with kind of one side of an equation, if you want to think about it that way. We didn't really have an equation, to be honest. Today, though, we're going to be working with equations. And our goal in just a little bit is to show that one side of the equation is equal to the other side using those trig identities that we had from 12.1. So it would work best if you had those kind of ready to go, because I probably will not go back to show you where they all were from 12.1. But make sure you've got those notes from 12.1 handy, because we're going to be using those frequently throughout today's notes. Now, some rules to follow, and really these are more things to try. The first one is the most important, is that you only get to use one side of the equation. So you don't get to just start working on both sides of the equation kind of all crazy like. You only get to work on one side. As a suggestion, it sounds weird, but pick the tougher side. If you pick the easier side, you might have less to work with than you do picking the more difficult side. Suggestion number 2 is, if you're kind of stuck working through a problem, change everything to be sine and cosine. And if you can try to get them all to be kind of one or the other, that usually works best. And then the third thing is, I know it's frustrating, but there are going to be some times where you're not exactly able to get it on the first try. And I know that's frustrating because we want it to be quick, we want it to be easy, but that's just not always going to be the case. And as I'm showing these to you, you have to understand that as I'm presenting them to you, there might be some times where I make mistakes, or I need to go back and I need to try it some other way, and that's okay. All right, so let's take a look at a few examples here. So example number 1, let's try to verify the identity that secant squared theta minus 1 is equal to secant, or divided by secant squared theta is equal to sine squared theta. Now, kind of using that number 1 rule to follow, we're going to pick one side of the equation to work with, and my suggestion to you would be this: let's pick the left side of the equation. Because starting with sine squared theta, sure, you can write a few things, but it's actually going to be quite a bit more difficult to get it to equal the left side than it's going to be to get the left side to equal the right side. So looking at that left side of your equation, you've got secant squared theta minus 1 divided by secant squared theta. Let's start by just thinking about some different ways that we could write that. And I'm going to actually show you 2 different ways that you can verify this identity. Now, the first way that I'm going to show you is to use a Pythagorean identity. Now, the Pythagorean identity that I'm going to use is that 1 plus tangent squared theta is equal to secant squared theta, which, by subtracting the 1 from the left side to the right side, tells you that tangent squared theta is equal to secant squared theta minus 1. Which means I can rewrite my numerator of the left side. So starting with our left side, secant squared theta minus 1 divided by secant squared theta, I can rewrite our numerator as tangent squared theta divided by secant squared theta. Which, not a whole lot helping us there. So let's do this. Let's try number 2 from above. So let's now try to change everything to being sines and cosines. So remember that tangent squared theta is the same as sine squared theta divided by cosine squared theta, divided by secant squared theta, which is 1 divided by the cosine squared theta. All right, so then let's just do a little bit of algebra. So let's rewrite this expression. Leaving sine squared theta over cosine squared theta, But instead of dividing by 1 divided by cosine squared theta, let's multiply by its reciprocal, which is cosine squared theta over 1, which then allows you to cancel out cosine squared theta and cosine squared theta, which leaves you with just sine squared theta over 1, or sine squared theta. And hey, guess what? That was what we wanted in the first place. Now, a second thing we could do, a second way that we could prove this, is actually less to do with some of the identities as just a little bit of algebra. So I'm just going to copy it down. So this will be the second way we could have worked that same problem. Is let's do this. Let's break apart our fraction. So let's rewrite it as secant squared theta over secant squared theta minus 1 over secant squared theta. Because then actually this will get us to the answer quicker than the first way. If you think about what secant squared theta divided by secant squared theta would be, that's just 1. And then 1 over secant squared theta is just a reciprocal identity. That's equal to cosine squared theta. And then that's actually one of our Pythagorean identities. 1 minus cosine squared theta is the same as sine squared theta. And actually just like that, we're already done. So it's kind of cool. There's a bunch of different ways that you can work through each of these problems, which kind of lets you have a little bit more freedom in how you work through them. Okay, let's take a look at another example. So example 2, let's now verify the identity that secant of x plus tangent of x is equal to cosine of x divided by 1 minus sine of x. And to do that, let's pick which side we're going to work with. So let's pick the right side and try to show that it's equal to the left side. So we're going to start with cosine of x divided by 1 minus sine of x. Okay. Now this is something that if you aren't really if you haven't practiced it before, you might not kind of see how it would work right away. And so this is where trying it multiple times can help you to kind of get a better feel for each of these problems. And there's little tricks that you can do as well. One of those little tricks that you can use is similar to multiplying by a conjugate. You can change the sign of what is in the middle. So with 1 minus sine of x, let's try multiplying by 1 plus sine of x in both numerator and denominator. Remember that that's okay so long as you multiply that in both the numerator and denominator. So let's go ahead and do that. We'll distribute our cosine of x to both terms. So that would be cosine of x plus cosine of x sine of x divided by, you're distributing here, 1 minus sine squared x. And if you needed to work that out kind of separately, you could. It would just be 1 plus sine x minus sine x minus sine squared x. And then the middle two terms cancel. And if you're familiar with multiplying by a conjugate, then that will make it a little bit faster for you to get there. Now, at this point, notice that the denominator, 1 minus sine squared x, is actually one of our Pythagorean identities. If you recall, 1 minus cosine squared x is this, or 1 minus sine squared x is the same as cosine squared x. Okay, well, we're getting closer. Let's go ahead and do a little bit more simplifying. So at this point, let's go ahead and break apart our fraction. So we'll have cosine of x over cosine squared x plus cosine of x sine of x divided by cosine squared x. Okay, getting a little bit closer. Let's do some simplifying. Cosine of x is going to cancel with one of these cosine of x's, so that leaves you with 1 over cosine of x. The second fraction, we're going to again cancel out cosine of x with one of these cosines of x, which gives you sine of x over cosine of x. And then now we've just about got it. 1 divided by cosine of x. We will use our reciprocal identity to rewrite that as secant of x. And then sine over cosine, remember that that is the same as tangent of x, which is what we wanted in the first place. And so we are done. Okay, if you felt comfortable with those two examples, I would say you can probably be done with this video. Feel free to hop on Big Ideas Math, do some practice with these. Obviously, I've got the extra practice worksheets there if you wanted to use those, work through it as well. If you don't quite get it yet, I've got another example. We're actually going to go through 4 more of these to help you understand it a little bit better. And then I will definitely at that point say that you're probably ready for the homework. So if you are sticking with me, we're going to be working through example 3. We've got 4 more equations that we're going to be verifying, and then we'll be done. Okay, so going through each of these, the first one that we are going to verify is that cotangent of negative theta is equal to the negative cotangent of theta. And let's go ahead and pick the right side, because the left side, we could probably work with it, but it might be a little bit more difficult. So negative cotangent of theta. Let's first just use the reciprocal identity to write that as 1 divided by negative tangent of theta. And then negative tangent of theta, we can then use our negative angle identity to rewrite that as 1 divided by the tangent of negative theta. So the negative angle identity lets us move the negative inside. And then, hey, guess what? That is exactly what cotangent of negative theta would be, and we are done. Okay, moving on to example B here. So this is example 3B. Let's first just see if there are any kind of identities that'll knock off some big stuff. In fact, before we do that, we probably need to pick which side we're going to work with. Let's pick the left side to work with since it's got a little bit more. Okay, so first thing I would notice looking at this is that 1 minus sine squared x looks kind of familiar. In fact, 1 minus sine squared x, remember, it is the same as cosine squared x. That was one of our Pythagorean identities. Now at this point, I'm a little bit stuck. So let's do this. Let's just, when we get stuck, change everything to be sines and cosines. So cosecant of squared x would be the same as 1 over sine squared x multiplied by cosine squared x. Which then if I put those together into a single fraction, I end up with cosine squared x divided by sine squared x, which is, when you use your special identities for cotangent and tangent, exactly the same as cotangent squared x. And we're done. Okay. So taking a look at C, I would say definitely the more difficult looking side would be the left side. There's a lot more to it. I think trying to start with a 1 and somehow end up with cosine of x, cosecant x, tangent x would be kind of difficult. So let's do this. Let's go ahead and, since there's really not a whole lot else we can do, let's just change everything to being sines and cosines. So obviously cosine of x are good there. Secant of x is 1 over sine of x. And tangent of x is sine of x over cosine of x. And I mean, you can kind of grind this out however much you want to. If you wanted to just put everything in the numerator together, then that becomes sine x, cosine x. Denominator is already sine of x, cosine of x. And hey, that's the exact same thing divided by itself. That does in fact equal 1. Okay, one more to look at here. So we've got tangent squared x plus 1 multiplied by cosine squared x minus 1 is equal to negative tangent squared x. Okay, so the first one, tangent squared x plus 1, we can actually, let's go ahead and, before I guess I get going, make sure that we're using the left side of the equation. But tangent squared x plus 1 can actually be simplified pretty quickly. That's a direct Pythagorean identity. That's equal to secant squared x. Now cosine squared x minus 1 is a little bit more difficult to see. So I'm just going to work this for you off to the side. We've got cosine squared x plus cosine squared x is equal to 1. That is our kind of starting off Pythagorean identity. What I want to do is I want to try to make it look like cosine of squared x minus 1, which I can do pretty easily moving the 1 over to the left side of the equation. So that gets me that sine squared x plus cosine squared x minus 1 is equal to 0. But now I want to get cosine squared x minus 1 by itself. So let's subtract the sine squared x over. That tells us that cosine squared x minus 1 is equal to negative sine squared x. So that's not really a Pythagorean identity, at least right off the bat. But using the Pythagorean identity, we can replace now in this equation that cosine squared x minus 1 with a negative sine squared x. So you might have to do a little bit of rearranging in some equations to get it to work the way you want it to. Now at this point, I really don't have a whole lot else I can do as far as identities go. So let's just use our reciprocal identities to rewrite secant squared x as 1 over cosine squared x multiplied by that negative sine squared x. Then we can write it as a single fraction, so negative sine squared x over cosine squared x. And hey, what do you know? Sine squared x divided by cosine squared x is tangent squared x. You get a negative in front, so negative tangent squared x, and you are done. All right, that wraps up 12.2. You should have homework on big ideas as well as a worksheet for extra practice that you can work on if you'd like to do a little bit more of this. And I think you might find that as you start to practice this a little bit more, they can actually start to be kind of fun to work through, and it's almost like a puzzle that you're trying to put together. So that being said, if you have any questions, feel free to drop by during office hours or shoot me an email. Otherwise, I will talk to you next time.